So if you watch this video that's playing on the left here previously, that's where I was producing an ambient noise sensor simulator box. And if you watch that, it'll give you a bit more of an insight into how ANSs work, and in particular what voltage you're expecting at this input terminal here. And that's shown in the manufacturer's manual. You're basically expecting a voltage between 1 and 4 volts. 1 being a very high ambient noise condition and 4 low, so it's kind of reversed to what you'd expect. And then if you fall outside this criteria, so less than 0.3 or more than 4.8 volts, then that's considered a fault condition. Likely of being one leg's dropped, or it's not seeing all the resistors basically in the circuit. So I thought that it might be useful if we could monitor that voltage on one ANS or multiple ANSs, and we could determine the average noise on a site somewhere over a longer period of time. And we could also monitor the audio broadcasts, so you can determine what level the broadcast is above the background noise and so on. Anyway, it's early stage, but what I thought I'd do is to feed that into a microcontroller, and I've decided on the ESP32 because that's my preference at the moment, and it supports Wi-Fi and Bluetooth and everything else, and it's very cheap. But a ESP32 only supports up to 3.3 volts on the input, okay? So we're going to have to do some kind of adjustment of this voltage, because we're going to expect something between, well, probably 0 to 5 volts, okay? So let's have a look. So assuming an input voltage then of 0 to 5 volts, and we want an output voltage which goes into our microcontroller of 0 to 3.3 volts, we somehow need to divide that down to get within that range, okay? And the maths is nice and easy on this, and there's a thing called a voltage divider circuit, which is one of the simplest circuits around, and it's basically a combination of resistors. So on this one, what I'm going to use is 2 resistors like this, okay? And this here, sorry I'm not drawing very well, will go to our ground or our 0 volt reference, and our input comes here. All right, that's our input voltage here, which is going to be in the range of 0 to 5 volts. And if I make this 100 kilo ohms and this 200 kilo ohms, then actually the voltage I get off here will be anything between, you know, if the input is between that and that, I'm going to get anything between 0 and 2/3 of 5, which is 3.3333 recurring, and so on. All right, so brilliant. That's, I know it's not quite 3.3, but it's good enough. All right. Now the issue is that you don't really want to be taking, oh, these are high resistors, but you don't really want to be taking this to ground through yet another resistor, because your reading here will be affected by it. So what we need to do is to create a much higher resistance or a high impedance input for the circuit. And the way to do that is to do a voltage follower circuit using an op-amp. Now op-amps are fantastic devices. This is the symbol for an op-amp. It's just a basic triangle, and it has what's called it's non-inverting input and an inverting input. Now, this is not the power supply to the device. The power supply is normally shown here, okay, and you have to have a plus voltage here and a negative voltage here in reference to this ground, all right? Now what an op-amp does is it tries to, whatever voltage I put in on this input, it will drive its output to do whatever it takes to make this net inverting input the same as that. So if you loop this back here to its input on the inverting input, whatever voltage I put here, it will drive this output to make this one match. Now that might seem a pretty pointless device or circuit, but actually this input here is very, very high impedance, so, you know, mega ohms, and this output here is quite low impedance, all right, so that we can use that to drive something else. So if we take this here and put it into that, and I think we'll do the same here, so our input coming here will come in via another op amp. There. So our 0 to 5 volts will come in here. Okay, and we will do a voltage follower circuit there. And rather than it coming direct from there, we will have it coming from here into our voltage divider circuit. Okay, and then that's our output there. Alright, so that's our voltage from the input terminal. Goes through a voltage follower circuit, so this is very high impedance input, very low impedance output, through our resistor network to divide the voltage down to the range we're after. Okay, and then that will go into another voltage follower circuit so that any load we're putting on here is not affecting this divider circuit, and that will give us a nice 3.0 to 3.3 volt output. Fantastic. And here it is. I've built the circuit up. It's not quite as simple as what I gave you on that noddy CAD sketch there. And the reason for that is, of course, you've got to produce your negative voltage. Now, you could do that by just putting two batteries together and taking the centre as your ground, but I just want to keep it simple with I'm going to go for a 7.2 volt lithium ion battery pack, and I want that to then be inverted to give me a minus 7.2 volts. So I'll have a plus 7.2 and a minus 7.2 volts, and of course my 0 volt reference. That's what I'm after. Okay, now there's a fantastic little device which is this fella here, and it does exactly that for you. Okay, so I won't go into the detail of how that works or what it is or anything like that, but these capacitors are associated with it, and of course these little jumper wires are as well. But all you got to know is that is giving me my minus voltage for this fella over here, which is the op amp. So this is a dual op amp. It's an 8-pin device, so it's got 2 lots of inverting inputs, 2 lots of non-inverted inputs, and 2 outputs. Basically, it's a pair of op amps in a single chip. And I've done exactly what I showed you on that little sketch, where it's coming in from your ANS connection there, and then into an op amp, out of that into my voltage divider, and then back into another op amp to give us a nice clean steady output, and then that gets fed into one of the input pins on this ESP32, and that's the pin you can see there coming in. Okay, now one other thing I have done is, just as a bit of added protection, I've used a Zener diode here. A Zener diode, if you've not heard of them, it's basically got a characteristic similar to a normal diode, but in reverse bias it breaks down at a specific voltage. So a normal diode is like that, yes, and in conventional current flow it will flow this direction, but it won't allow it to flow in this direction. Okay, it will eventually if you put enough voltage in there, but then you're doing damage to the diode probably, putting too much higher voltage through it. With a Zener diode, the symbol is actually very similar, but it's got a little kick like that. I think it's supposed to look a bit like a Z. Okay, and again it does that. It will allow the voltage to pass, a current pass this way, but not this way, up until a specific voltage, and they are quite specific. Now I bought a kit of them, look. And there are all kinds of voltage options here. So look, there's a, I don't know if you can see that, that's a 3.6 Zener diode, a 4.3 volt diode, 12 volt, and so on. So they break down in reverse bias, in other words going this way, at a specific voltage. So the idea is on this circuit, anything above 3.3 volt, because I don't want more than 3.3 volts going into there, is going to pass through this Zener diode and take it to ground. Okay, so one extra bit of precaution I've done on here is that prior to coming into this Zener diode is another 10k resistor. If I go back to that original sketch here, so this output now is going into a 10k resistor, okay, then into my Zener diode, which is reverse bias, and then that goes to ground, and then I take my output from here, okay, into my ESP32. Alright, so what happens is the output from here, if it goes above 3.3, then anything that's above 3.3 volts will pass through that diode, but because it's going through 10k, then it won't be a huge amount of current. It's not going to do any damage. If it's below 3.3, then all of the current will pass through here and into your ESP32 and onto the I/O pin. Okay, so it regulates it. Now, actually, these are quite cheap Zener diodes, and the reverse bias sort of breakdown is not clean, if you like, and it curves off quite early. So what you probably want on an ideal Zener diode is if you've got voltage here and current here, let's say this is sort of 1, 2, 3, 4 volts, and 1, 2, 3, 4 volts, and that's 3.3, say there. What you would want is like absolutely no current to pass through it, and then it to do that. Boom. It allows infinite current, if you like. But actually they're not like that. They tend to curve something like that, you know, and then it's just be a gradual curve going up. All right. So I didn't want this to occur. I didn't want it to constrain the current, or start to allow current to flow at anything below 3.3. So I've actually had to go for a Zener diode at 5.1 volts to be well out of this curve here. So my curve on my 5.1 probably starts something here, yeah, and then goes up. But I'm guessing that if I buy higher quality Zener diodes, then this curve won't be as flat like that. It will probably be much sharper curve, and then I can get a lower value. But anyway, it works fine. I've measured it, so that's all good. Okay, in case you're wondering what these things are, well, they are just little voltage selectors. So this one is set to 100k, and this one is set to 200k. So you move these jumpers, and you can get any value you like out of it. They're not that precise, but for this breadboarding thing, they're fantastic because you've got all the resistor values you could want are selectable from here and here. So when you're playing around, rather than keep changing resistor, you can just reprogram the value, if you like, just by moving the jumpers. So these are giving me my voltage divider circuit effectively. And this here, well, I don't actually have an ANS to hand right now, so I can't produce that output from the ANS that you'd get at that point there. So I've just got a potentiometer, and it will drive this output voltage to that sort of 0 to 5 volt range. The board is currently powered from here, and I'm driving that at 7.2 volts, as I said. That's what I'm aiming for. And that device there will give me a minus 7.2 volts as well. Okay, and then all of the blue pins along here and here and here, they're all the 0 volt ground reference, which ties in with this ESP32 ground as well. So all the circuit now is taking whatever I choose from turning this potentiometer, the input voltage, and coming into this GPIO pin here. Okay, so just to jump the gun a bit, let's see what we're going to do with that data before we look at this board in a bit more detail. Right, so here you go. So ESP32 is running some code I've put together. It's monitoring this pin, and again I'm using the Blink.io platform, and it's transmitted it over the cloud services, and then I've put together this user interface here. So as I adjust the potentiometer, which is simulating an ANS, you can see my dB level going up and down. All right. Meanwhile, the graph here, which is recording the history, is going up and down with it. I've also got a voltage reading here. Probably won't have that in the final device, but at the moment it's nice to be able to see that. And then you may recall that an ANS has two modes of settings, two ranges it can be. So you've got a low range, which is 55 to 85 dB, and a high range, which is 65 to 95 dB, all right? So most of our ANS should be set to low. I see so many of them set to high, but they should really be low. It's unlikely that your ambient noise is going to be above 85. So, but if you did have it set to high, well, if you just click that and you'll see this adjusts automatically. So it's now telling it, well, my ANS is actually set to high. Can you use that value, please? But I'm going to put it back to low. There you go. So this all looks good. I'm telling you live exactly what dB reading is evaluated from that voltage coming in from the ANS. I'm recording it here in some history, and there's tools that we'll look at later to analyse that in more detail. And also I've got this fault here. So if you remember, if we go down below 0.3, it should be a fault. So if I take this voltage down to below 0.3, then the fault LED comes on. Now I don't go into fault straight away. I wait for at least 10 iterations of it being below 0.3. That's why there's a slight delay. Otherwise, you might get a few false reports of it being fault. And then let's get it out of fault again. There you go, it's gone. And then it's up above 4.8 is also a fault condition. So let's get it up there. There you go, it's come on. And then go back down. Okay. There you go. So that's, I guess, the first prototype of this concept. And hopefully I'm going to come up with a few more ideas how we can sniff off, well, actually, is this the ambient noise I'm hearing, or is there a broadcast going off? Okay, so going to have to take that into account. Going to have to be able to extract this data to give a average over much longer periods of time, and perhaps produce a report from it. Anyway, let's see where this goes. All right, catch you later.